The magical arrangement of the universe, 2. Hello and welcome to my channel. In the universe, the Earth seems to have a customized fit. From the macroscopic to the microscopic, a variety of seemingly accidental physical and chemical conditions have come together to create a habitable world. Why is the Earth's crust just thick enough to allow the movement of tectonic plates to produce a rich variety of landscapes and ecosystems? Why do the peculiar properties of water make ice less dense than liquid water, allowing lakes and oceans to sustain life in the cold? Why is the concentration of oxygen sufficient to support biological respiration without causing catastrophic combustion? Why does the composition of the atmosphere shield the planet from deadly radiation and maintain the greenhouse effect, saving the planet from extreme weather? Not only that, but the types and properties of the chemical elements in the periodic table seem to be just right to form the basis of life, allowing complex biochemistry to function. The soil structure skillfully supports plant growth, laying the foundation for the entire ecosystem, and the salinity of the oceans maintains a delicate balance that ensures the survival of marine life. All of this may seem random, but it's as if there is some kind of tacit agreement between the universe and the Earth that allows life to flourish and thrive. Today we are going to show 8 amazing arrangements of the universe. 11. Thickness of the Earth's crust. Why does it support plate movement? How thick is the Earth's crust and why is it just right to support plate movement? This question may sound a bit philosophical, but it is actually a delicate balance in nature, which seems to be coincidental and orchestrated by nature. In order to understand the problem of just the right thickness of the Earth's crust, we must first understand how the Earth is made up. The Earth's interior can be divided into several layers. The outermost is the crust, below is the mantle, and then the outer and inner cores. The Earth's crust, on which we humans depend for our survival, varies in thickness from a few kilometers to tens of kilometers, and on average is about 30 kilometers thick. However, this thickness is not constant. There are 2 types of crust: continental crust, which is usually between 30 and 70 kilometers thick, and oceanic crust, which is thinner, around 5 to 10 kilometers. It seems that the thickness of the crust varies quite a bit, but regardless of the type of crust, it has one common characteristic. It is thick enough and thin enough to withstand just enough of the forces within the Earth to be able to generate power to support the movement of the plates at the same time. If there is such a wide variation in the thickness of the Earth's crust, why is it still able to support plate tectonic movement? First of all, the theory of plate tectonics itself is like a big trick of the Earth, which can explain various natural phenomena such as earthquakes, volcanoes, and the formation of mountains. At the heart of plate tectonic movement is the idea that the Earth's crust is made up of several plates of varying sizes that float on the deeper mantle, and that they are constantly moving as they collide with, separate from, and rub against each other. The just right here is that the crust must be of the right thickness, neither too thin nor too thick. If it is too thin, the momentum of plate movement will not be enough to push the crust to change significantly. If it is too thick, the crust will become too hard, and the movement between the plates will be difficult to occur or occur very slowly. In fact, the evolution of crustal thickness from the formation of the Earth to the present day is a dynamic process that has created favorable conditions for current plate tectonics. In order to figure out the relationship between crustal thickness and plate motion, scientists have made a lot of efforts, especially at the beginning of the 20th century, when research on the crust and mantle progressed by leaps and bounds. At that time, a key breakthrough was the exploration of the Earth's interior through seismic waves. Through the speed of seismic wave propagation in different media, scientists were able to deduce the structure of the Earth's inner layers, including the thickness of the crust. One of the famous scientists, Alfred Wegener, proposed the doctrine of continental drift, which was not widely accepted initially, but laid the foundation for the later theory of plate tectonics. And by the 1960s, oceanographers and seismologists gradually revealed the distribution of crustal thickness and the interrelationships between the crust and the mantle through deep-sea exploration, seismic wave surveys, and large-scale geological investigations. This process is like a jigsaw puzzle that slowly reveals the inside view of the Earth. For example, in the study of oceanic plates, Scientists have found that the thickness of oceanic crust is generally thinner, which explains why oceanic crust is more active and subject to more frequent earthquakes and volcanic activity. The thicker crust of continental plates, on the other hand, is relatively more stable, but where it is moderately thick, it can also withstand the collisions and friction between plates, which in turn produces geological phenomena such as mountain ranges and deep ocean trenches. Not only is the Earth's crust just the right thickness, but its materials and structure also provide support for plate movement. In fact, the Earth's crust is not as static as we might think. It is somewhat elastic, adapting to changes in the Earth's internal forces. This elasticity is just another manifestation of the thickness of the crust, just right. Scientists point out that this elasticity of the crust comes from its composition, mainly a combination of minerals such as silicon, oxygen, aluminum, and iron. Continental crust floats high on the Earth's surface because it contains more granite-like material, which is lighter than oceanic crust. Oceanic crust, on the other hand, is relatively heavy and sits below sea level because it contains more basalt, which is denser. The movement of the plates is not just pushing and pulling, it also involves squeezing and spreading of the crust. For example, at some plate junctions, the crust will be deformed due to internal forces, and even plate subduction will occur in some cases, which cannot be realized without proper crustal thickness. Let's take a real example to feel how this just right thickness works. For example, the famous Himalayan region. The Himalayas were formed by the collision of the Indian and Eurasian tectonic plates. In fact, the collision of these two plates has a very long history, and there are complex geological formations on their contact surfaces. As early as hundreds of millions of years ago, the Indian plate had begun to contact with the Eurasian plate. In the process, the Indian plate sinking, the Eurasian plate continues to squeeze, and finally in the junction of the two plates formed the Himalayas. What is more interesting is that this collision process is not an instantaneous thing, but slow and continuous. It is because of the moderate thickness of the Earth's crust. The force between the plates can be in a long time in the collision of the formation of the scale of huge mountain ranges. Today, the Himalayas, as we see them, are actually continuing to rise, growing by about 5 millimeters per year, which is a vivid reflection of plate movement. This example shows very well how the thickness of the Earth's crust affects plate movement, which determines not only whether a collision can occur, but also the outcome of the collision. For example, if the crust is too thin, the collision may lead to violent fracture. If it is too thick, the friction between the plates may be too great, resulting in the plates not being able to make effective contact and, ultimately, natural phenomena such as mountain ranges and volcanoes cannot be produced. As science and technology continue to advance, the relationship between crustal thickness and plate motion remains an active area of research. Scientists have been able to further measure and explore the changes in the thickness of the Earth's crust in different parts of the planet, and even how they adjust over time and with environmental changes through a variety of means such as seismic waves, satellite remote sensing, and ocean drilling. These studies not only help us to understand the formation process of the Earth, but also help us to predict some natural disasters and avoid or minimize the losses caused by them. For example, by studying the correlation between the thickness of the Earth's crust and seismic activity, scientists have found that areas with more frequent seismic activity are usually places with thinner or more active crusts, while some areas with thicker crusts are relatively stable. This not only provides us with an early warning system for natural hazards, but also provides more evidence of the Earth's ingenious, just right design. Why is the thickness of the Earth's crust just right to support plate movement? From a scientific point of view, it is the result of the long-term evolution of the Earth, the formation conditions of the Earth, the composition of the crust, the dynamics of the plate, and other factors work together to create such a just right thickness. The thickness of the Earth's crust can not only ensure the movement between the plates, but also avoid excessive deformation or collapse, providing a stable living environment for life on Earth. This is an ingenious arrangement of nature and a natural mystery that scientists are gradually unraveling. 12. Properties of water. Why is ice less dense than water? The peculiar properties of water not only make some phenomena in our daily life possible, but also further deepen mankind's profound understanding of nature. Why does the ice of water float on the surface? Why does life on Earth survive in winter? All this is closely related to the low density of ice. First of all, it must be recognized that the performance of water in most cases is quite conventional. The liquid state, it is dense, mobile, can help plants absorb nutrients. Flowing water can also take away heat and dissolved oxygen. But once the water becomes ice, this seemingly simple transformation will actually make its physical properties undergo a series of surprising changes. We know that when water turns to ice, it becomes less dense and thus floats on the surface. This phenomenon is one of the unique things about water as a substance. Imagine if ice was denser than water, then it would sink to the bottom after freezing. What would happen? When winter comes, lakes and rivers would be covered with a thick layer of ice, and the ice on the surface of the body of water would completely isolate the water below, and organisms below the surface would freeze to death, and the entire ecosystem could collapse. Fortunately, the ice floats on the surface of the water, and the ice isolates the cold air from further infiltration, allowing the temperature of the water below the surface to be maintained at a more stable range. And the organisms are still able to survive the cold winter months. This ingenious design makes water a more stable environment for life on Earth. So why is ice less dense than water? Let's start with the molecular structure of water. A water molecule, H2O, consists of 2 hydrogen atoms and 1 oxygen atom, and in liquid water, these molecules are connected to each other by hydrogen bonds. Hydrogen bonding is a rather specialized type of chemical bonding, similar to the attraction of a magnet, but it is much weaker than normal chemical bonding. When water changes from a liquid to a solid state, aka ice, the hydrogen bonds between water molecules form a regular 3-dimensional structure that actually consists of an arrangement of many hexagons. This structure has one remarkable feature: it creates more gaps between the molecules, resulting in a larger average distance between each molecule than in liquid water. The presence of such voids means that the molecules of ice are more loosely arranged, resulting in ice being less dense than water. As water changes from liquid to ice, the water molecules increase in size and decrease in density, with the result that ice floats on top of the water. If ice were denser than water, as most substances are, then when water freezes, it sinks into the water, and the world would be extremely different. This phenomenon was first noticed in ancient times. The phenomenon of ice floating on water was used by the ancients to explain why rivers and lakes were not completely frozen in winter. However, scientists did not begin to study the difference between the ice and liquid states of water more systematically until the 17th century. Peter van Misgenbroek, a 17th-century Dutch physicist, first drew attention to changes in the density of ice when he studied the thermal expansion of water. But it wasn't until the mid-19th century that French scientist Jean-Baptiste Biot explained in more detail the reasons for the different densities of ice and water. As thermodynamics and molecular theory continued to develop, scientists gradually revealed the molecular structure of ice and how it affects its density. You can imagine how difficult it was for these scientists to study this problem. They didn't have the advanced instruments that we have today, and many of their conclusions were reached through precise experiments, careful observation, and the slow accumulation of data. Behind the seemingly simple low density of ice, there are in fact extremely complex molecular motion and thermodynamic principles in support. Ice density lower than water is not just a strange phenomenon, it has an extremely important ecological significance. For example, we can look at the Arctic ecosystem. The Arctic sea ice covers vast areas of the ocean, and this ice provides a natural insulating layer for the water, keeping it within a suitable temperature range. This environment allows Arctic marine life, such as seals and whales, to acclimatize to the frigid waters and survive. At the same time, the buoyancy of the ice affects the circulation of the water. The ice on the surface of the water stops the loss of heat, and this insulation allows the lower layers of the water column to remain warmer, especially during cold seasons, when organisms are still able to find survivable temperatures underwater. In the absence of this phenomenon, the entire body of water may freeze, and even organisms in deeper water may lose their habitat as the ice forms. In addition, ice floating on the surface of the water plays an important role in the regulation of the Earth's climate. Ice reflects large amounts of sunlight through the effect of high albedo, effectively regulating the temperature of the Earth's surface. If ice were denser than water, it could sink to the bottom, leading to changes in the process of heat exchange between the oceans and the atmosphere, which in turn would affect the stability of the global climate. Let's imagine again that if ice were denser than water, that would mean that many bodies of water, such as large lakes and rivers, would freeze completely solid in winter. But most bodies of water on Earth don't freeze completely at extremely cold temperatures. The reason why water stays in a liquid state is because ice is less dense, floats on top of the water, and forms a thin shell of ice. This ice shell is like a warm quilt. It insulates the outside world from the cold, so that the body of water underneath can still be maintained in the temperature range close to the freezing point. This liquid window allows many aquatic organisms to survive the harsh winters. This phenomenon is particularly important in the Arctic, Antarctic, and alpine lakes around the world. In Arctic glacial lakes, for example, the temperature of the water beneath the ice remains around 0 degrees Celsius all year round, which is just the right temperature to allow certain aquatic organisms, such as ice fish and certain algae, to survive. This means that the low density of ice actually provides space for what we call winter aquatic ecology. This property of water also allows one to marvel at the ingenuity of nature's design. It is like a delicate balance that allows the Earth's ecosystems to maintain their diversity and stability. This just right characteristic not only guarantees the existence of life on Earth, but also provides us with endless space to reflect on our deep connection with nature, with physics, and with chemistry. 13. Oxygen concentration. Why is it just right to support biological respiration? Why is it that the concentration of oxygen on Earth is always just right to meet our and other organisms' needs for survival? In fact, this seemingly simple oxygen concentration is backed by nature's exquisite regulation and the accumulation of billions of years of evolution. First, we need to understand the composition of the Earth's atmosphere. The Earth's atmosphere can be roughly divided into several gases, of which the main components are nitrogen, about 78%, oxygen, about 21%, and some other gases, such as argon, carbon dioxide, water vapor, and so on. To put it simply, oxygen is not a particularly high percentage of the Earth's atmosphere, but it is this just right percentage that allows biodiversity and life to flourish. Imagine if the concentration of oxygen is too high, the oxygen in the air will become extremely active, which may lead to some oxidizing reactions are too violent, and even lead to disasters such as fires. And the cells of living organisms may be damaged due to too much oxygen. If the oxygen concentration is too low, the organisms cannot get enough oxygen, respiration will be limited, the energy in the organism cannot be effectively supplied, the organisms will face starvation and death. So, how is the oxygen concentration just right? Let us unravel this mystery from the history of the Earth and the evolution of life. Oxygen concentration on Earth did not start out as stable as it is today. In fact, the Earth's early atmosphere had virtually zero oxygen and consisted entirely of carbon dioxide, nitrogen, ammonia, and so on. This period, which lasted for about billions of years, was also a time when life gradually developed some simple forms in this oxygen-free environment. Over time, the earliest photosynthesizing organisms, cyanobacteria, appeared on Earth. These cyanobacteria used solar energy to convert carbon dioxide and water into oxygen and sugar in a process called photosynthesis. Initially, the oxygen produced by the cyanobacteria was absorbed by the iron in the water, but over time, the oxygen gradually accumulated in the atmosphere, changing the Earth's atmosphere. About 2.4 billion years ago, the concentration of oxygen in the Earth's atmosphere began to rise significantly, an event known as the Great Oxidation Event. This turning point meant that oxygen was no longer a scarce substance in the Earth's atmosphere, but became a key component in supporting complex life. Now back to our question, why was oxygen concentration just right to support biological respiration. This is a complex balancing act between the Earth's atmosphere, the evolution of life, and chemical reactions. The just right oxygen concentration comes first from the ratio of nitrogen to oxygen in the atmosphere. Nitrogen is the most abundant gas in the Earth's atmosphere, occupying almost 78% of the atmosphere. Its presence makes the atmosphere more stable and prevents oxygen from overreacting with other substances. The concentration of oxygen is kept at about 21%, which is enough to support effective respiration of animals and plants on Earth, but not too high to cause uncontrolled oxidation reactions. On the other hand, the just right concentration of oxygen is also closely related to the Earth's carbon cycle. Plants absorb carbon dioxide and release oxygen through photosynthesis. Animals breathe in oxygen and convert it to carbon dioxide. This cycle keeps the oxygen concentration in a stable range. The concentration of oxygen in the atmosphere is influenced by the interactions of biological and geological activities as well as chemical reactions, and over a long period of time, an equilibrium has gradually been found that is suitable for life on Earth. The just right oxygen concentration is not only due to the stabilizing effect of nitrogen, but it is also closely related to the Earth's oxygen management system. This system consists of several key components: photosynthesis, respiration, geological processes, and the effects of human activities. 1. Photosynthesis. As mentioned earlier, plants, cyanobacteria, and other photosynthetic organisms use sunlight to convert carbon dioxide and water into oxygen. This process is the main source of oxygen production. As plants and phytoplankton expand, the concentration of oxygen in the Earth's atmosphere gradually increases. 2. Respiration. Animals and other aerobic organisms form a network of material exchange between organisms by inhaling oxygen and releasing carbon dioxide. Without sufficient oxygen, the metabolism of these organisms cannot proceed and the energy supply is interrupted. 3. Geological processes. There is also a subtle exchange of oxygen between the Earth's lithosphere and the atmosphere. For example, volcanic activity releases gases, mainly carbon dioxide, while atmospheric oxygen reacts with minerals in the Earth's crust to regulate the composition of the atmosphere. In addition, biochemical cycles within the Earth also regulate the concentration of oxygen in the atmosphere. 4. Human activities. Although human industrial activities have some effect on atmospheric oxygen concentrations, these changes are short-term and are not sufficient to change the base level of atmospheric oxygen concentrations. However, as global warming and activities such as deforestation increase, rising carbon dioxide concentrations may affect photosynthesis and the oxygen cycle. So the long-term effects of human activities on oxygen concentrations remain an issue that requires close attention. The ability to keep oxygen concentrations just right is also closely linked to the Earth's climate and environmental conditions. As you can imagine, if the Earth were a little farther from the sun, the temperature would be too low, the water would freeze, and photosynthesis would not be able to take place efficiently. Conversely, a little closer to the sun, the Earth would be too warm, bodies of water would evaporate, and carbon dioxide concentrations would be too high, which could also inhibit photosynthesis. The Earth's atmosphere also acts as a climate regulator. Greenhouse gases in the atmosphere, e.g., carbon dioxide, methane, etc., help to keep the Earth's temperature within the appropriate range. Without these greenhouse gases, the Earth would be a cold planet, where photosynthesis could not take place and oxygen production would be impossible. By analyzing the Earth's history and current oxygen concentrations, scientists have found that the metabolism of living organisms is severely affected if oxygen concentrations fall below 20% or less. Many organisms, especially mammals, will show symptoms of asphyxiation or even die due to lack of oxygen. And if the oxygen concentration exceeds 30%, the oxidizing property of oxygen becomes so strong that it can even lead to oxygen toxicity, which can lead to cell damage and death in severe cases. Therefore, the oxygen concentration is maintained at about 21%, just right. It supports aerobic respiration and also avoids the adverse effects of excess oxygen. And the stabilization of this concentration is the result of the fine-tuning of the Earth's complex ecosystems and atmospheric chemical cycles. 14. Atmospheric composition. Why does it protect life? The atmosphere exists and is composed as if it were customized for us, not only to provide oxygen and temperature regulation for life on Earth, but also to create conditions for organisms to survive in a number of ways. It is a profound and mysterious balance, like a perfect design in nature's careful planning. First, let's look at the composition of Earth's atmosphere. The Earth's atmosphere can be roughly divided into nitrogen, 78%, oxygen, 21%, argon, 0.93%, and traces of carbon dioxide, neon, helium, and methane, according to the type of gas. The composition itself is somewhat just right. As we know, nitrogen occupies the vast majority of the atmosphere, and it neither supports life's respiration nor participates in biochemical reactions. Nitrogen actually acts as a stabilizer, keeping the atmosphere stable and preventing an excess of oxygen. Then there is oxygen, which makes up about 21% of the atmosphere, a seemingly simple ratio that is just right for the activities of animals and plants on Earth. Too low a concentration of oxygen prevents organisms from breathing effectively, while too high a concentration leads to excessive oxidizing reactions that cause damage to living things. Therefore, an oxygen concentration of 21% is just right. In addition, there are trace gases, such as carbon dioxide, which, although not a large percentage of the atmosphere, plays a key role in the global climate and life support systems. Carbon dioxide helps the Earth maintain warm temperatures and prevents it from becoming too cold. Without it and other greenhouse gases, Earth might be a frozen planet. The proportions of these gases, nitrogen, oxygen, carbon dioxide, and others, in the Earth's atmosphere are just right for life to exist and evolve. The role of the atmosphere can literally be described as a shield for the existence of life. Without it, life on Earth might not exist at all. It not only protects us from external radiation, but also regulates the temperature to keep the Earth within a temperature range suitable for life. 1. Radiation protection. The atmosphere acts as a giant shield to help protect us from cosmic rays and solar radiation. While the ultraviolet rays emitted by the sun, especially UVA and UVB rays, are vital to the physiological activities of living organisms on Earth, without the ozone layer in the atmosphere to filter these radiations, the intensity of the UV radiation would be too intense and could lead to serious genetic mutations or even render life on Earth unviable. This is not alarmist talk. In fact, the Earth's ozone layer has been protecting us by keeping harmful UV rays from reaching the ground directly. The ozone layer absorbs a great deal of ultraviolet radiation, especially UVB, reducing damage to biological DNA. If the ozone layer is destroyed, we will face more diseases such as skin cancer and eye problems, which may also have fatal effects on other organisms in the ecosystem. 2. Temperature regulation role. Another key role of the atmosphere is temperature regulation. We often talk about the greenhouse effect, which actually refers to the phenomenon that greenhouse gases such as carbon dioxide and methane in the atmosphere absorb and re-radiate heat. This phenomenon keeps the surface of the Earth warm. Without the presence of these greenhouse gases, the average temperature of the Earth could drop to -18 degrees Celsius, which would be unviable for the vast majority of life. This is why the temperature on Earth is always kept within a range suitable for life. Radiation from the sun enters the atmosphere. Some of the heat is absorbed by the atmosphere, some is reflected back into the atmosphere by the ground, and then released back to the Earth's surface by greenhouse gases. This process acts as a natural temperature regulator, ensuring that there is enough heat on the Earth's surface to sustain life's activities. However, the greenhouse effect has its just right side. If the concentration of greenhouse gases is too high, it could lead to an excessive rise in global temperatures, leading to catastrophic consequences such as climate change and sea level rise, while if the concentration of these gases is too low, the Earth could be plunged into a bitterly cold ice age. Fortunately, the Earth's atmosphere is just right to allow the greenhouse effect to stabilize and stay within a temperature range suitable for life. 3. Oxygen supply. Just the right concentration. As far as oxygen is concerned, the concentration of oxygen in the atmosphere is about 21%, a ratio that is ideal for aerobically breathing life forms. If the concentration of oxygen is too high, the cells of living organisms may suffer oxidative damage or even oxygen toxicity, whereas if the concentration is too low, respiratory difficulties will result and life will not be able to obtain sufficient energy. This just right concentration is the key to the survival of all aerobic organisms on Earth. On Earth, the cycle of oxygen is mainly maintained by photosynthesis in plants and respiration in animals. Plants absorb carbon dioxide and release oxygen, while animals inhale oxygen and exhale carbon dioxide to maintain their life activities. This process is continually cycled through a complex ecosystem, ensuring that the concentration of oxygen in the atmosphere is within a range suitable for life. 4. Biodiversity support. The composition of the atmosphere not only plays a key role in sustaining life, it also creates an environment that supports biodiversity. The delicate balance of multiple gases allows the Earth's climate, environment, and ecosystems to maintain their complexity. Different biomes, including land, sea, and airborne microorganisms, all of which thrive under the shelter of the atmosphere. For example, plants in forests absorb carbon dioxide and release oxygen through photosynthesis, which not only provides oxygen, but also regulates atmospheric humidity through transpiration. Atmospheric water vapor and clouds likewise play a crucial role in regulating temperature, precipitation, and so on. And different living species depend on specific climatic conditions and atmospheric composition to maintain the stability and balance of the ecosystem. I'm afraid it's hard to believe that the just right atmospheric composition is a coincidence. Scientists have studied the atmospheres of other planets, notably Mars and Venus, and found that their climatic conditions are far too different from Earth's to support the existence of complex life. Mars has a very thin atmosphere with almost no oxygen and an excessively high concentration of carbon dioxide. Venus' atmosphere, on the other hand, is made up of large amounts of carbon dioxide and thick clouds, resulting in surface temperatures as high as 460 degrees Celsius, far beyond what life can tolerate. In contrast, the composition and structure of the Earth's atmosphere seems so perfect and just right. So, is this a coincidence or some kind of inevitable result? From a scientific point of view, the Earth's oxygen concentration, temperature regulation, and radiation protection is indeed the product of billions of years of evolution. Life on Earth and the atmospheric system have found this just right balance through long-term interaction and mutual influence. This equilibrium is the result of the long evolutionary history of the Earth, but also closely linked to the stable radiation of the Sun, the protection of the Earth's magnetic field, and other factors. The Earth's atmosphere is a kind of patron saint. It not only provides us with oxygen to breathe, but also shields us from the Sun's harmful radiation, regulates temperature, and protects life. We live every day in this seemingly ordinary air, breathing oxygen, feel the warmth, but seldom stop to think about how just right it all is. 15. The periodic table of the elements. Why are the types and properties of elements suitable for life? The periodic table of the elements. Why are the types and properties of elements just right for life? When this question is posed, it feels like we are entering into a huge puzzle. In fact, the kinds and properties of those elements in the periodic table, especially those we know as carbon, hydrogen, oxygen, and nitrogen, are literally like the perfect puzzle pieces needed for life, and their interactions provide support for life. What is the mystery behind this? Let's begin to unravel this question by looking at the wonderful world of the chemical elements. If you pick up a copy of the periodic table of the elements, you'll notice that it looks like a beautiful, well-organized map. Each element is in its place quietly waiting to interact with other elements. The rows, cycles, and columns, groups, of the periodic table skillfully categorize the elements according to their atomic structure and chemical properties. The types and arrangement of elements in the periodic table are not random. Their properties, reactivity, stability, and bonding properties are just right to make life on Earth possible. Let's start with the most basic building blocks of life: carbon, hydrogen, oxygen, and nitrogen. Whether human, animal, or plant, the chemical basis of life is made up of these elements. They make up the most important molecules in our bodies: proteins, nucleic acids, DNA and RNA, fats, and carbohydrates. Carbon is one of the most unusual in the periodic table of elements. It has 6 protons in its nucleus, 6 neutrons, and 4 electrons on the outside. This electron configuration makes carbon particularly well-suited to forming a wide range of chemical bonds, especially covalent bonds with other carbon atoms. The strength and stability of this covalent bonding provides the possibility for carbon to build the long-chain structures that are the basis of organic molecules in the living body. Carbon can be combined with other elements by forming single, double, and triple bonds to build extremely complex molecular structures, making it the element of choice for the composition of organic compounds. Carbon's ability to do this is unmatched by other elements. Silicon, for example, is chemically similar to carbon, but its bonds are not as flexible as carbon's, and the molecular structures it forms are not as stable as carbon-based molecules. Therefore, although in science fiction we often imagine that extraterrestrial life could be based on silicon, in reality, silicon-based life is far less stable and diverse than carbon-based life. Carbon's just right is also reflected in its range of existence. Carbon is one of the most common elements on Earth, and its atomic structure allows it to combine with other elements such as hydrogen, oxygen, and nitrogen while remaining stable in aqueous solutions. Carbon is therefore the building block of all living things, from the simplest single-celled organisms to the most complex multicellular organisms, where it plays a ubiquitous role. Hydrogen is the lightest element in the universe, with only 1 proton and 1 electron in its nucleus. Hydrogen is very chemically active and combines easily with other elements, especially oxygen and carbon. The hydrogen atom is the basic component of the water molecule, H2O, which in turn is the basis for the existence of life. Whether it is metabolic reactions inside the cell or physiological activities outside, water plays a crucial role. Hydrogen combines with oxygen to form water, giving life its fluidity and variability. Water is a very unique solvent, capable of dissolving a wide range of chemicals, allowing chemical reactions within life to proceed smoothly. The vast majority of biochemical reactions within life occur in aqueous solutions. Without water, many of life's reactions simply could not take place. Not only that, but the combination of hydrogen and carbon also provides us with a source of energy. Organic compounds such as glucose and fats in the body of life almost always contain large amounts of hydrogen and carbon, which release energy through reactions with oxygen to support life activities. It can be said that hydrogen plays a crucial role as a gas pedal in the energy metabolism of life. Oxygen is one of the most important gases in the Earth's atmosphere. It is not only an important component of the air, but also vital to all aerobic life forms. Oxygen's atomic structure makes it highly electronegative, enabling it to combine with other elements, especially hydrogen, to form water molecules. Oxygen plays a central role in respiration. Animals and plants do this by inhaling oxygen, converting it into carbon dioxide and water, and releasing energy in a process called aerobic respiration. This process is called aerobic respiration, and the energy released during this process is the source of life-sustaining activities. Oxygen is just right because it is chemically active. When combined with other elements, oxygen is able to participate in a large number of redox reactions, releasing energy, but it is not so active that it leads to excessive oxidation and cell damage. This balance makes oxygen the most suitable respiratory gas for life forms on Earth. Nitrogen is the main component of the Earth's atmosphere, making up about 78% of it. Although nitrogen itself is not directly involved in biological respiration, it is the basic element of life molecules such as amino acids, proteins, and DNA. Through chemical reactions, nitrogen atoms, along with elements such as carbon, hydrogen, and oxygen, make up the most important molecules in the body of life. The presence of nitrogen also helps maintain stability in the Earth's atmosphere. Nitrogen is chemically inert and does not react easily with other elements, which makes it act as a stabilizer in the atmosphere, preventing oxygen concentrations from being too high or too low, thus maintaining atmospheric balance. The origin and evolution of life cannot be separated from the interaction between elements. As we have seen, life on Earth is based on the construction of carbon, hydrogen, oxygen, nitrogen, and other elements, and the chemical properties of these elements enable them to combine and decompose efficiently to build the complex molecular structure of life. Almost all of these chemical reactions take place in the unique solvent of water, which itself happens to be a combination of hydrogen and oxygen. The just right nature of these elements is closely related to their atomic structure, electronic configuration, and chemical reactivity. Their stability and diversity provide the basis for life, while their reactivity powers the various metabolic reactions within life. Not only that, but the relative proportions of these elements on Earth are also very appropriate. For example, the ratio of oxygen to nitrogen in the atmosphere makes the Earth a suitable place for life, and the presence of water allows these elements to stabilize in solution and participate in reactions. The arrangement of the periodic table of chemical elements may appear to be a simple arrangement of numbers, but behind it lies the code of life. Each element of the periodic table seems to provide the necessary parts for the construction of life. Their chemical properties complement each other, making possible the phenomenon we call life today. The arrangement of profiles in the periodic table corresponds to the diversity and stability of chemical reactions. From the simplest hydrogen to the most complex elements, each element in the periodic table supports, in its own way, the existence of life, one of the most complex and amazing phenomena in the universe. 16. Soil structure. Why it favors plant growth. Soil structure. Why is it just right to support plant growth? As soon as this question is posed, it seems to touch directly on a seemingly simple but complex and mysterious part of nature. Soil, that seemingly mundane thing, turns out to be the cornerstone that supports plant growth on Earth. If you think about it, the composition of soil, its structure, the nutrients and water it contains, seem to be customized by nature for plant growth. We often think of soil as just a pile of mud that we can just scrape up, but it's actually much more complex than we realize. The basic components of soil can be divided into 4 main groups: minerals, organic matter, water, and air. Each part is essential for plant growth, and their ratio is very just right. 1. Minerals. The skeleton of the soil. The minerals in soil come from the weathering of rocks. Over millions of years of weathering and erosion, rock fragments are refined into particles of sand, clay, silt, etc. that form the soil we see today. Different types of soil contain different sizes and types of mineral particles, usually including sand, clay, and silt. For example, sandy soils have large particles that drain well but hold water poorly, making it difficult for plant roots to find enough water in them. Clay particles, on the other hand, are very fine, do not lose water easily and retain water well, but are also difficult for roots to penetrate if they are too dense, resulting in oxygen not being able to enter the soil. This creates a just right problem. The proportion of sand and clay, if adjusted appropriately, you can make the soil both water retention and do not let the water stagnation for too long, not only to provide the oxygen needed by the root system, but also to ensure that the plant absorbs sufficient water. 2. Organic matter, the soil's source of life. Organic matter refers to the humus in the soil, which comes from plant and animal remains that decompose in the soil and become nutrients that plants can absorb. Humus is very important to the soil because it increases the fertility of the soil and provides nutrients such as nitrogen, phosphorus, and potassium that plants need to grow. At the same time, humus serves to improve the structure of the soil. It makes the soil looser, improves soil aeration, and also helps the soil retain water. This makes it easier for the plant's root system to absorb water and nutrients. The balance is also just right: too little organic matter, and the soil lacks the necessary nutrients. Too much organic matter can lead to acidification of the soil, which limits the oxygen supply to the roots. Therefore, the content of organic matter in the soil should be moderate in order to effectively promote plant growth. 3. Water. The life fluid of soil. Water is the indispensable liquid of life for plant growth. Soil water comes from precipitation and groundwater recharge. Plants absorb water through the root system and use it for photosynthesis and other physiological processes. However, there should not be too much or too little moisture. With too much moisture, the soil will become devoid of oxygen and the root system will have difficulty in breathing, which may lead to root rot. With too little moisture, the plant will not be able to get enough water for photosynthesis and metabolic activities. Therefore, the soil must have just the right amount of drainage and water retention. This balance is the key to soil structure. 4. Air. The breathing space in the soil. In the soil, it is not only water and nutrients that are essential for plants, but also the oxygen in the air. Plant roots need oxygen to respire, release energy, and support growth. If the soil is not well aerated, the root system will be deprived of oxygen, resulting in plant roots not being able to breathe properly and growth being restricted. Air in the soil comes mainly from water voids. In a suitable soil structure, there is a very good distribution of water and air between the soil particles. A sandy soil has good air circulation because of its larger particles, but it retains water poorly, while a clay soil does the opposite, retaining water well, but with poor air circulation. A medium-textured loam, with the right proportion of sand, clay, and organic matter, and just the right amount of aeration and water retention, is an ideal soil for plant growth. Interestingly, the plant root system itself is also a mixer of soil structure. By growing and expanding, the plant root system constantly changes the structure of the soil. For example, roots penetrate the soil during growth, breaking up some of the tighter soil structures and creating a looser root space, which not only helps the plant to obtain more nutrients and water, but also promotes air circulation in the soil. Additionally, roots dissolve minerals in the soil by secreting organic acids, making nutrients in the soil more readily available for uptake. They even help break down organic matter in the soil through symbiosis with microorganisms, further enhancing the fertility and structure of the soil. This root-soil interaction also illustrates that soil and plants are a mutually reinforcing system. Roots help keep the soil loose and the soil provides support and nutrients to the roots, and this interaction is the basis for plant growth. Microorganisms in the soil, such as bacteria, fungi, and other microscopic organisms, also play an important role. These microbes help break down organic matter and facilitate the cycling of nutrients. Microbes do this by breaking down plant debris and converting it into nutrients that plants can absorb. They also help plants to defend themselves against pathogens, forming a natural immune system. The activity of microorganisms also promotes soil fertility and permeability, making the soil more suitable for plant growth. Especially in the process of organic matter decomposition, microorganisms will produce some substances that can improve the soil structure, such as humus, which not only provides nutrients for plants, but also improves the water retention and aeration of the soil. Every part of the soil, from its mineral composition to its organic matter to its water-to-air ratio, supports plant growth. And the ratios of these elements are just right to allow plants to take root, absorb water and nutrients, and grow and reproduce successfully in the soil. If there is too much or too little of a particular component in the soil, plant growth will suffer. For example, too much water in the soil can lead to a lack of oxygen and even rotting of the root system, while too little water will not be able to meet the plant's growth needs. The organic matter in the soil also needs to be maintained in a certain proportion. Too much can lead to acidification of the soil, while too little may lack sufficient nutrients. Poor air circulation can lead to suffocation of the plant roots and prevent them from breathing properly. This balance is exactly what nature has skillfully arranged. A dynamic, interdependent ecosystem is formed between the structure and composition of the soil and the plant root system. Plants change the structure of the soil by interacting with it through their root systems, and the soil in turn supports plant growth by providing nutrients, water, and air. In general, the relationship between soil structure and plant growth can be described as just right. Soil is more than a simple physical support. It is a living ecosystem. Each soil particle has its own role to play in regulating the distribution of water, air, and nutrients to support the healthy growth of plant roots. 17. Ocean salinity. Why does it maintain ecological balance? Have you ever wondered how the salt in the oceans actually plays a silent but vital role in supporting the Earth's ecological balance? Seemingly simple as salt, there is a complex ecological relationship in nature behind it all, and it's just right. If the salinity of seawater were a little higher or lower, the marine ecosystems we see now might not be the same as we know them to be. Today, let's explore the mystery of ocean salinity from the perspective of just right. Ocean salinity refers to the concentration of dissolved salts in seawater. Generally speaking, the salinity of ocean water is about 35 per thousand. That is to say, there are about 35 grams of dissolved salt in 1 kilogram of seawater. This value fluctuates from one ocean to another. For example, tropical oceans have relatively high salinity, while some near-polar oceans have low salinity, but in general, the salinity of the global ocean stays within a relatively stable range. This 35 per thousand salinity value may seem ordinary, but it is the key to maintaining the ecological balance of the ocean and the stability of the Earth's atmosphere and climate. Since the salinity can affect the ecological balance, then how it is just right. Let's talk about it from the perspective of marine life. The vast majority of organisms on Earth live in freshwater, and waters with low salinity are the most suitable environment for them to live. However, marine organisms are able to live in high-salt environments, and some species can even thrive in areas where the salinity of the water varies greatly. Behind this is a biologically marvelous mechanism called osmoregulation. Simply put, marine organisms regulate the balance of water and salt in a high-salt environment through mechanisms in their bodies. For example, fish will remove excess salt from their bodies through organs such as kidneys and glands, while maintaining sufficient water. This regulatory mechanism is the result of evolution, allowing marine organisms to adapt to this particular environment. The development of this adaptation, in turn, happens to be closely related to the salinity of the seawater. If the salinity is too high, many marine organisms will find it difficult to survive, but if the salinity is too low, many species adapted to high-salt environments will not be able to survive. Therefore, the just right salinity of seawater provides an ideal living space for various marine species. From an atmospheric perspective, the just right salinity of the oceans is also directly related to the Earth's climate and weather cycles. As you may know, the oceans are the largest heat regulator on Earth. When the surface of the ocean absorbs sunlight, the water temperature rises and the heat is transferred around the world through ocean circulation, affecting climate patterns. However, ocean salinity is closely linked to the ocean's thermohaline circulation. The density of water increases in areas of higher ocean salinity, so the water in these areas tends to sink, creating deep-sea currents, while areas of lower salinity float, creating surface flows of ocean water. This salinity-induced difference in density drives the global thermohaline circulation, which we know as the oceanic circulation. This circulation system not only affects the distribution of ocean temperatures, but also directly influences the Earth's climate. For example, the North Atlantic warm current is through the thermohaline circulation to regulate the flow of warm water to the Arctic region to ensure the warm climate of Europe. Behind this, changes in salinity play a crucial role. If the salinity of the ocean changes, the speed and direction of the thermohaline circulation will also be affected, which in turn will have a huge impact on the global climate. Not only that, the salinity of the seawater also regulates the pH, i.e. acidity and alkalinity, of the water body to some extent. This regulation helps maintain the stability of marine ecosystems. Marine waters are usually weakly alkaline, and the salt in seawater absorbs or releases hydrogen ions through chemical reactions that help maintain a relatively stable pH. If the salinity of seawater changes, the pH of the water may also change, affecting chemical reactions in the ocean and even threatening the survival of marine life. For example, corals, shellfish, and some marine plankton are very sensitive to the pH of water. A balance of salinity and pH is like providing a stable habitat for these marine organisms. Digging a little deeper into the conversation, salinity changes are also closely linked to climate change. As global warming increases, polar glaciers are melting at an accelerated rate, and the flow of melted freshwater into the oceans is causing salinity to decrease in some areas. This decrease in salinity affects the pattern of ocean circulation, which in turn affects the climate system. For example, the melting of ice in the Arctic, while appearing to be an increase in water resources, reduces the salinity of seawater and affects the stability of the thermohaline circulation. Such changes could lead to warmer or cooler temperatures in some areas and could even alter the path of storms. Scientists have already found that climate change is already altering the salinity distribution of the global oceans, especially at high latitudes, and that such changes could affect the strength of the oceanic circulation, which in turn could trigger global climate change. The impact of ocean salinity on the entire marine ecosystem is most directly reflected in the establishment of food chains. As we move from the microscopic to the macroscopic, from phytoplankton to large marine mammals, every link in the marine food chain is maintained in a relatively stable state under the influence of salinity. Phytoplankton are the foundation of the marine ecosystem, absorbing sunlight, carbon dioxide, and providing energy for the entire marine food chain through photosynthesis. Zooplankton, e.g., zooplankton, crustaceans, then serve as their food chain link, and larger animals, such as fish, whales, and sharks, rely on these tiny beings as a food source. If there is a change in salinity, the living conditions of the plankton will be affected. In the case of phytoplankton, for example, if the salinity of seawater becomes too high or too low, their ability to grow and reproduce will be inhibited, which in turn affects the stability of the entire food chain. In other words, if the salinity is not just right, the entire marine food chain can be disrupted. Ocean salinity is also closely related to the cycling of chemicals in the water. Salt in seawater is not simply sodium and chlorine, but also contains many minerals that are essential to the growth of marine life, such as calcium, magnesium, potassium, and sulfate. These minerals are involved in the exchange and circulation of materials in the ocean through the action of the salinity of seawater and the water cycle. Calcium and carbonate, in particular, play a vital role in the growth of marine life, especially corals and shellfish. Corals build their skeletons by absorbing calcium and carbonate ions from the water. If the salinity changes, the concentration of these chemicals will also be affected, which directly leads to the limitation of coral growth and affects the balance of the whole marine ecology. Through this series of analysis, it is easy to see that ocean salinity plays a crucial role in maintaining the ecological balance of the Earth. It not only affects the survival and reproduction of marine organisms, but also is closely related to global climate, atmospheric circulation, material exchange, and other aspects of the system. This salinity, through its just right ratio, maintains the stability of marine ecosystems. 18. The Earth's magnetic field. Why is it just strong enough to protect life? When you look up at the night sky or sit on your balcony with the breeze blowing, thinking about how everything on Earth is taken for granted, few of you may notice that an invisible shield is always silently guarding us. That is the Earth's magnetic field. You may be thinking, isn't a magnetic field just an invisible force, like an electromagnet or a compass? How can it be linked to the protection of life on Earth? Actually, this invisible magnetic field is much more important than you think. It is not just a natural phenomenon of the Earth, but its strength and nature happen to form a barrier that protects life. Without it, life on Earth might have long ago failed to adapt to the environment we know today. First of all, to understand why the Earth's magnetic field is so vital to life, we have to start with its source, the Earth's core. The Earth's core consists of two main parts, the outer core and the inner core. The outer core is liquid, consisting mainly of metals such as iron and nickel, and is extremely hot, close to the Earth's core temperature. The inner core, on the other hand, is solid, also composed of iron and nickel, and exhibits a hard structure. It is from the flow of molten metal in the outer core that the Earth's magnetic field is generated. Simply put, the Earth's outer core has a large amount of liquid metal, especially iron and nickel, moving at high speeds, creating an electric current. The electric current then creates a powerful magnetic field based on the principle of electromagnetic induction. This magnetic field is not static, but varies as the Earth rotates, creating an extremely complex and dynamic system of electrical currents that produces what we call the Earth's magnetic field. It is like a giant magnet, forming a strong, magnetic shield around the Earth, separating the Earth from the surrounding space. So why is the strength of this magnetic field just right? If it is too strong, it may interfere with electrical equipment on Earth and may even affect the evolution of living things. If it is too weak, the Earth will not be able to effectively defend against radiation from space. Scientists have found that the strength of the Earth's magnetic field is closely related to the rate of matter flow in the outer core. The strength of the magnetic field at Earth's surface is about 25 to 65 microtesla T. In comparison, planets like Jupiter have magnetic fields about 20 times stronger than Earth's, while Venus and Mars have almost no magnetic field. If Earth's magnetic field were too strong, it could pose a threat to life. We can give an example. A strong magnetic field would cause more energetic charged particles to be trapped within the Earth's magnetosphere, and these particles would produce intense radiation that could affect the genetic structure of life, or even lead to cell damage or mutation. And if the magnetic field is too weak, it can effectively keep out high-energy particles from the solar wind and cosmic radiation, which can damage the Earth's atmosphere and may even deprive the planet of moisture and atmosphere, making it as inhospitable as Mars. But fortunately, the Earth's magnetic field is just the right strength. It effectively shields the solar wind from charged particles without unduly interfering with life on Earth. Scientists call this phenomenon the golden zone of the magnetic field. This, like an invisible, protective shield, not only to ensure that the Earth is free from external radiation, but also does not allow the magnetic field itself to have a negative impact on living things. The solar wind is made up of charged particles released by the sun, which continue to spread outward, traveling through space and hitting the Earth. Without the barrier of the Earth's magnetic field, these charged particles would hit the Earth's atmosphere directly, with devastating consequences. Worse, if these particles in the solar wind were to impact directly on the Earth's surface, they could cause the Earth's atmosphere to peel away, ultimately depriving the planet of its protective atmosphere and water resources. The Earth's magnetic field prevents charged particles in the solar wind from hitting the Earth by directing them to the polar regions. You may have noticed that the aurora borealis is a product of this process. When charged particles from the solar wind are directed to the Earth's poles by the magnetic field, they collide with oxygen and nitrogen in the atmosphere, creating the beautiful phenomenon of the aurora borealis. At the same time, the Earth's magnetic field effectively protects our climate system. Without this protective layer, the Earth's atmosphere might have been stripped away long ago, and the climate would have become so extreme that life would never have survived. Once, scientists, by studying the history of Mars, found that after the disappearance of the magnetic field of Mars, the climate gradually became cold and dry, and the water source gradually evaporated to nothing, and eventually turned into the current barren scene. But here is an interesting point, that is, the Earth's magnetic field is not completely stable. The strength of the Earth's magnetic field fluctuates and even reverses. We are now familiar with the North Pole and South Pole. In fact, once exchanged positions, scientists call this phenomenon magnetic pole reversal or geomagnetic reversal. Geomagnetic reversal. These reversals are frequent but do not occur very quickly, and each magnetic reversal can take thousands or even tens of thousands of years, with little effect on the Earth's ecosystem. Scientists have also found by studying the geologic record that the strength of the Earth's magnetic field used to fluctuate dramatically, sometimes getting stronger and sometimes getting weaker. Fortunately, however, the Earth's magnetic field has not disappeared completely, and it varies within a stable range. It is in this relatively stable magnetic environment that the evolution of our species and other life has taken place. The Earth's magnetic field not only protects life from the solar wind, it is also closely linked to the Earth's atmosphere. Scientists have discovered that the formation and maintenance of the Earth's atmosphere is closely linked to the Earth's magnetic field. Magnetic fields slow the stripping effect of the solar wind on the atmosphere, especially in the Earth's upper atmosphere, reducing the loss of hydrogen and oxygen from the atmosphere. In addition, the Earth's magnetic field serves to prevent cosmic radiation from hitting the Earth directly. Cosmic radiation consists of a large number of energetic particles that come from the sun and outer space. Without the protection of the Earth's magnetic field, these energetic particles could enter the atmosphere and damage the DNA in cells, increasing the incidence of diseases such as cancer. Studies have shown that other planets such as Mars and Venus have suffered severe radiation erosion of their atmospheres due to the lack of effective magnetic field protection, making it impossible for them to maintain the climatic conditions necessary for life. In contrast, the Earth's magnetic field acts as a powerful shield, providing a safe space for life. What does the Earth's magnetic field have to do with our daily lives, you may ask? In fact, its influence has quietly penetrated into various fields. Many high-tech devices in modern society, such as satellite navigation systems and communication facilities, rely on the precise measurement and understanding of the magnetic field. Slight changes in the Earth's magnetic field can even affect the normal operation of these devices. In addition, geomagnetic storms are a manifestation of changes in the strength of the Earth's magnetic field. When solar activity is high, the solar wind can cause strong geomagnetic storms. Although the Earth's magnetic field can effectively withstand these storms, they can still have an impact on power networks and communication systems at high latitudes. Fortunately, the Earth's magnetic field is generally stabilized within a suitable range of strength, so geomagnetic storms can cause some temporary disruptions, but for the most part, they do not pose a threat to life on Earth. Well, that's it for this installment of the program. Welcome to like and comment. Thanks for watching.